Hello and Assalamu alaikum dear students. So yesterday we had studied quasi-linear first order partial differential equations, and if you remember we have uh, discussed how these type of equations can be solved using a methodology which was based on that theorem, that we have to find some two functions u and v from the equivalent system of ordinary differential equations, which is equation 5. And to solve this system and find u and v, we had also completed two examples, example 4 and example 5, and we had applied, if you remember, the methodology of lecture 4 in first module, that was method 2. So using method 2 we know that how to solve the system of the ordinary differential equations of the type dx over p is equal to dy over q is equal to dz over r. Now today I will try to explain you how can we solve initial value problem of quasi-linear first order partial differential equations, and how this theorem can be implemented on initial value problem of a quasi-linear first order partial differential equation. But before that, let's just formally discuss how first order partial differential equation, which is quasi-linear, and its initial value problems looks alike. So this is a theorem. The theorem which is theorem 6. This is not included as a proof, but the statement of that theorem is included. So the statement says that, let's just focus on the statement and we will try to use that theorem in order to solve initial value problem of quasi-linear partial differential equation. So let us say that a of x, y, z, b of x, y, z and c of x, y, z, which were the coefficients and the right hand side in equation 1, have continuous first order partial derivative with respect to x, y and z, and let the initial curve C be described parametrically. If you remember, I had given you a video lecture in which I have described that we actually parameterize the initial curve and also the obtained characteristic curves. So the characteristic curve is parameterized with respect to the parameter t, and initial curve is parameterized with respect to the parameter s. So let the initial curve be parametrically given as x of s, y of s and z of s. This is the curve from which your surface passes. What is your surface? Your surface is the solution z. Z is your required solution and this is the surface. So that surface passes from the initial curve, which is x of s, y of s, z of s. We don't know what is the surface, but yet we can parametrically give the solution of z. Z depends upon xy, and we will give the solution of x, y and z independently in terms of another parameter, which is t. So this is the initial curve. Initial curve has a continuous tangent vector, and we suppose that this quantity is non-zero, which is called Jacobian. If you remember that, what do you mean by Jacobian? Since you are having look, okay, so this is the derivative of dy over ds of a minus dx over ds of multiply by sorry, not of a, this is dy over ds a minus dx over ds b. So that Jacobian of the transformation, basically Jacobian is calculated for any transformation. Now we are dealing with the parameter s, so this will be called j of s, and this has to be non-zero. What is j? Actually, let us write formally that what is j. So j, which is Jacobian, sorry, capital J, which is Jacobian, is defined as a determinant. So how can you write the determinant? I will try to write in that software. So determinant of the matrix. What is the matrix? Matrix is yeah, there is a matrix. So matrix first entry will be what? The first entry can be it is written here. So yes, it is dy over ds, not there, and that can be dx over ds, dx over ds, and that can be b and a, and that can be b. So this is your Jacobian of the transformation. Okay, so this determinant has to be non-zero. We will come to that, because you must know why this determinant must be non-zero. But initially just focus on that fact that we have supposed that quantity is non-zero in equation 10. Basically this j of s represent the tangent vector, actually tangent vector for the initial curve C, and that vector has to be non-zero. Then there exists a unique solution z defined in some neighborhood for the initial curve C. So actually if this determinant is non-zero, then there exists a unique solution for the system, one that satisfies the partial differential equation. This is analogous of what we have already studied for the initial value problem in ordinary differential equations, which was there. We assume that the functions are piecewise continuous and smooth and do not vanish at all points. So that point which says that do not vanish at all points is actually taken care by this quantity, which was j of s. Since derivatives are not zero, it means that tangents are not zero. So continuous tangent vector, and that slope is not zero. This is the theorem which says that the problem will have a unique solution for initial value problem. Now the question is, how can you solve this problem using the theorem, which was theorem I think 2. Yes, theorem 5, using theorem 5. So actually I will explain this methodology using some example, because there are several things which you must understand for that particular problem. So let's focus on the problem. Okay, so this is the initial value problem. Partial z over partial y plus z partial z over partial x is equal to 0, and z of x 0 is f of x. This is the initial value problem of quasi-linear partial differential equation. So what is the first step? You have to find the characteristic curves. Characteristic curves are which curves? The equations which were said dx over dt is a, dy by dt is b, and dz by dt is c. Okay, but before that, in the first step, you must parameterize the initial curve. Look back on the theorem that we have just now studied. The statement initial value problem must be parameterized in that form. So the initial curve is what? The initial curve is given as this z of x comma 0 is f of x, which means that z is your required solution, which is function of xy. But when y is 0, your surface becomes a curve which is f of x. This is called the initial curve. I repeat again, z of xy is your original solution, but if you take instead of y equal to 0, this will be now a curve which is called f of x, any function is equal to z. So this is now a curve, initial curve, which means. And now how can you parameterize? You can parameterize by using some parameter. Look, If you take x equal to s, you have to use the parameter s, not t, not w, not r, not p. We have focused and fixed the parameter which is s for initial curve. So now x, if x is the parameter s, then y will be what? Y is identically 0, so there will be no effect on y, because y, we have taken y equal to 0. Y is always 0. What will be the effect on z? Z will become f of s, because x is replaced by s. This is the procedure to parameterize. If you go back to the theory, the same we have done there in the theorem statement. What we have done? X of s is x. So what is x of s is? X of s is s. This is your x of s. Y of s is 0 and z of s is f of s. So this is the way to parameterize your initial curve. The next, actually the first step is you have to find the characteristic equations. The characteristic equations are, we know that from quasi-linear theory, dx over dt is a, dy by dt is b, and dz by dt is c. Now the solution is very easy, because they can be solved separately. Look, if you concentrate on dz by dt, so how can you solve? Integrate both sides. What will be the answer? Z is a constant. We have named this constant as C3 of s. Look, very importantly, that now I am writing there, the characteristic equations are not like that. I am sorry, I have written in very not suitable form. I am writing there, dx over dt is a is what? A is your z, and similarly dy by dt is b. B is what? Just focus on the coefficient of partial z over partial y in the equation. So partial z over partial y has a coefficient 1. So dy by dt will be 1. And lastly, the third one is dz by dt will be c, and c on the right hand side is not present, so that will be 0. But these are characteristic equations in terms of t, and I have told you earlier that you have to find the solution in parametric form. How can you find in parametric form your solution? So required solution, I am writing just for your knowledge. Required solution will be, so required solution will be what? In parametric form. So in parametric form, mathematically parametric forms are written like that: x of t, okay, this is not correct, but let's focus on that, y of t and z of t. This is the way to write the solution, but this is the way to write the solution only when you are not given initial value problem. But since you are given initial value problem, you must also insert the parameters which was used for initial value problem. So the parameter which was used for initial value problem was s. So this will be function in general of s comma t. This will be function in general of s comma t, and this also will be function of s comma t. So now the answers of these ordinary differential equations will be in terms of x of s comma t. So you must write here s comma t, x is function of s comma t, y is function of s comma t, and z is function of s comma t. Okay, very nice. Now yeah, you have to solve this. This is very easy to solve, because now dz by dt can be solved. Look, the answer is z is equal to some constant. The name of the constant is c3, but remember that your z was function of s comma t. So you are integrating with respect to t. This was repeated in ordinary differential equation course as well. So now the constant of integration will not be any real number, that will be constant other than t. So other than t we have s. So any function of s will be your constant, because with respect to t everything has been integrated. The thing which has left behind except t is s, so there will be a constant. Now if you integrate both sides, the answer will be t plus another constant c2, uh, which is again s. So now y is found out, z is found out. Now in order to find the variable x, what you will do, you put the value of z. If you put the value of z here, from there the answer will be zt plus. It is not better to write zt, because look, z can be any variable and it depends upon t. So this will be part of your integration. It is not suitable. Instead you must put c3, because since z is constant with respect to t, so we can do that. I mean to say, look, dx by dt equal to z. If z is function of s comma t also. So if you integrate both sides, what you will get? Integrating both sides, you will get x equal to integral of z. So in general you don't know the answer. In general, and now I was saying that dx over dt is z, and if you integrate both sides, there will be on the right hand side integral of something which is z, which is function of st dt. With respect to t you are integrating, plus some constant, we are naming that c1. Okay, we are naming that c1. Now since z is in general function of t, you cannot take z outside of the integral. This was I am repeating since the previous semester. You cannot write this integral as like that, because z depends upon t. But you know now that z is constant, since derivative of z is 0. So with respect to t, we have no problem. With respect to t, z is constant, and the answer we know that okay, I write there. Answer, we know that z of s comma t, the answer is c3. We have written already in the PDF. So this step you must be take care of that. Now you can take integral from out of the integral. You can write c3 instead, and now it is easy to and it is permissible to write z in outside the integral, and the answer will be what? Answer will be c3 t plus c1. Okay, c1. Instead of c3 I have directly written z. So that is your answer in the PDF lectures. Don't hesitate yourself. I have explained every step. But the actual steps are that you have to take care of z. Z is not constant with respect to t in general. In that particular example, it is constant, but in general it is not. So you must put the value and then integrate. Okay. Now the second step is that you have to apply the initial conditions, just like in ordinary differential equations we apply the conditions. So how using Laplace transform, if you remember, we have applied already the conditions. So now how can you solve this? Actually, if you remember, we have solved initial value problems of system of ordinary differential equations in previous class, if you remember. And we have applied Laplace transform to solve two simultaneous linear ordinary differential equations. These are three simultaneous linear ordinary differential equations. Look, and there are three conditions: one for x, one for y, and one for z. That is why you can use that knowledge also, but in if you don't know that, you can use initial value problem. So initial value problem was that initially we have parameterized already the initial curve. So what do you mean by initial curve? Initial curve means that, if you remember from ordinary differential equation knowledge, we always said one thing, that at t equal to 0, y is 1. at t equal to 1, y prime, sorry, if you remember for Laplace transformations, y prime is 2, and we have already solved second order ordinary differential equations. This was the initial this was also, so this was initial value problem for one initial value which was 0. Now there also you must understand that you are doing initial value problem. So initial value problem means at t equal to 0 your function becomes initial curve. Generally, to solve ordinary differential equations you get curve and initial values are points, but partial differential equations you get the solution surface and initial values are curves. So this is one dimensionless. Since we have here points 0, 1, 0, 1, 0, 2, but on the partial differential equation side we have the points which are not points, they are initial curves. So actually indeed our initial condition becomes what? It remains similar, but instead of x equal to s you must write x of s comma 0, because at t equal to 0 you have x transformed into s, okay, and at t equal to 0 you have y transformed in terms of s, but indeed this is 0, and at t equal to 0 you have z transformed in terms of s, and again that is a function of s. So if you apply these conditions in these three solutions, at t equal to 0 the answer on the left hand side is for x is s, and on the right hand side is c1, so the answer of c1 will be s. If you put t equal to 0 here, the answer on the left hand side will be 0, because y of s comma 0 is 0, and on the right hand side you will get c2, so identically c2 is also 0, and last z, if you put t equal to 0 you will get c3, which is f of s. So if you apply the conditions, the answer of x, y, t can be very easily x, y equal to these type of solutions. The next step 3, writing the parametric form of solution. You should remember that you have to tell the solution in parametric form. So parametrically x is zt plus s, which is f of st plus s, because the value of z is f of s. The value of y is t, similar, because we have found here, look, by putting initial value problem, and z is also f of s. The next step is very important. You have to eliminate x and y, eliminate s and t, and write the solution in terms of x, y, because z generally originally was function of x, y. If you write z in terms of look, we have transformed z in terms of st, but if you write x is function of st, y is function of st, so z will also be function of st, but you have to go back as well. So can you go back? The question is, are you allowed to go back? This is the main problem in mathematics, that you must know that there is a rule from which you can go back. So can you go back? The answer is yes, you can go back from z in terms of st to z in terms of xy if you can eliminate the variables s and t. So how can you eliminate? This is chapter 9 chapter 2 or 3 of class 9, that you remember how to eliminate. Put the values wherever in z there is t or s, put the value of s and t in terms of xy. So there is s, how can you write s in terms of xy? Is there any way? Look, there is a way. S can be written as x minus zy. Look, s can be written as x minus tfs, and t is equal to y, so s can be written as x minus tf of s, or x minus yz, because you can also use z, no problem. So the answer of s is there, so z of st will be f of x, any function of x minus zy. That is your final answer. So this is the methodology from where you can solve initial value problems of quasi-linear partial differential equation. The next example, which is also related to quasi-linear partial differential equations. So if you focus on that problem, A is Z, B is Y, and C is X. So step 1 was just you have to parameterize the initial curve, but I think I have not parameterized initially. Yet you can use the parameterization. Here A is Z, B, Y, and C is X. So the characteristic equations are this, this, and this. And parametrically, when t is 0, x of s comma 0 is s, y of s comma 0. You can use this language as well, is 1, and z of s comma 0 for z condition is 2s. So now, which ordinary differential equation can be solved easily? This ordinary equation or this or this? Look, you have dx by dt is z. You don't know z, you cannot calculate the value of x. dy by dt is y. You cannot easily, yes, you can easily actually. Dy by dt is y, so dy over y is equal to dt. Integrating both sides, you will get y is equal to e to power t plus some constant as well, because these are ordinary differential equations and you know how to solve ordinary differential equations. There are 3 ordinary differential equations and 3 conditions, that's it, and they are simultaneous. So either you can apply Laplace transform on all 3 equations and use the given conditions, 3 conditions, but instead you can separately also solve. The answer of that will be what? So I am solving just for you. Dy by dt equal to y. So instead you can write as well, what you can write, dy over y equal to dt. So integrating both sides, if you integrate both sides, you will get the answer y log of y equal exponential of t. Okay, now sorry, not exponential, this is the second step, t, and y will be what? Y will be y of indeed s of t will be equal to e to power t. So this is the final answer, and this is the answer for your variable y. Now you know y. Dx over dt is written in terms of z. You cannot independently solve because you don't know z. And again, dz by dt is in terms of x. You cannot independently solve. So what you can do actually? You can easily do one thing, that either you must differentiate dx by dt with respect to t one more time, and on the right hand side you will have dz by dt, and dz by dt is x. You understand? Dz by dt is x. So look, there are 2 equations. One is, so there are 2 equations. One is dx by dt is z, and dz by dt is y. Sorry, dz by dt is x. So you can do one more thing, that differentiate either this or this with respect to t, what you will get. So we are differentiating this with respect to t. So the answer will be what? The answer will be d square over dt square, and on the right hand side you will have dz by dt. But you know that dz by dt is actually x, so this has to be eliminated, and the answer is indeed dx by, sorry, only x. Or you can do one more thing, that is equal to 0. So now you can, this is linear first order, second order ordinary differential equation, and you can use, if you remember that, put x equal to e to power mt. So the answer of two values of m will be there, that is the auxiliary equation m square minus 1 equal to 0. So the values of m are plus minus 1. Okay, now if you m has values plus minus 1, so the solution of x of s comma t will be what? The answer will be c1. Okay, so c1 of s, because again just concentrate on the thing that you have integrated with respect to t, c1 e to power t plus c2 e to power t minus t. Okay, minus t. Okay, now what can be z? Z is actually derivative of x. Look, this is given. You can use this equation or you can use this as well. So what can be z? Z of s comma t will be what? The same thing, but since this is the derivative, so exponential derivative is similar, but instead there will be minus. And you have two conditions. How you can solve these two conditions? For x, you have x of s comma 0 is actually what is? The answer is 2 sorry s. So the answer will be what? On the right hand side you will get c1 of s and c2 of s, because e to power 0 is 1. Similarly here you will have two conditions for z of s comma 0. The answer on the right hand side, we know that the condition is 2s. So 2s will be equal to, again if you put the value t equal to 0, the answer will be this, but just with the minus. So these are again two simultaneous equations, not now linear, in terms of c1 and c2. Variables are c1 and c2. So if you calculate easily, you can get the answer. For c1, if you add both equations, you will get c1 equal to 3s, and c2 can be 3s minus 2s s. So c1 will be 3s and c2 will be s, because c2 will be c1 minus 2s, so c2 will be s. This is your final answer. And parametrically you can write x of st, y of st, first of all write in that language parametrically, because sometimes you make mistakes in terms of going back. I have written directly step 4, that expressing z in terms of xy, but you must write parametric form of the solution as well. So first of all write parametric form. How can you write parametric form? X of st is what? X of st now becomes c1, the answer of c1 is 3s, and answer of c2 is s. So the answer will be what? Answer will be, so c1 is 3s, and c2 is s. So the answer is this. Now what will be the second quantity? Okay, I think yes, it is now better. Just wait 1 minute, I am trying to write in more suitable form. Okay, I think no. Okay, we can fix that. The notation is not correct, so look, yeah, now it's okay. X of s comma t is equal to that, and now y of s comma t is equal to what? We know that from the previous, because y was very easy. Y was what? Y was there. Okay, y is e to power t. Okay, because at t equal to 0 the answer is y is equal to 1, so the coefficient will be actually 1, so we are not writing that coefficient. because C1 1 multiplied by e to power t is e to power t. So the answer is e to power t for y. And the third one is z of s comma t. The answer is similar to that but with minus. Similar to that but with minus. This is parametric form. You must write this parametric form. I have not written that in the solution. This is actually very short form of the solution, but I have explained the solution on the math type tab. You can see there. And now you have to eliminate s and t and write the solution in terms of xy. I have explained this all methodology there, and this is your exercise to eliminate s and t and find the solution in terms of xy. It's very easy. Wherever s and t exist, write the expression in terms of x and y, and I have written that you must know how to eliminate the variables, and this is your exercise to do that. So these are the practice problems 1 to 5, and this lecture has been completed in 2 video tutorials. And now you all know how to solve linear for first order partial differential equation, method of characteristics, and method of characteristics for quasi-linear first order partial differential equations is now today ended. In the next lecture, in the next video lecture, I will explain to you how you can solve any nonlinear, because remember one thing, quasi-linear equations are also nonlinear, but they are very lightly, so to say, nonlinear equations. You can use any method of characteristics to solve them, but there are some problems which are highly nonlinear, and there is a method of characteristics regarding these type of nonlinear partial differential equations. So I will try to explain you this method also, and then we will move on towards second order partial differential equations. Thank you very much for listening. Please attempt the problems by yourself and try to solve all 5 problems. Thank you very much.